Hello, everyone. Welcome to your lecture on normalization of database tables. And in this lecture, we will learn what normalization is and what role it plays in the database design process. We'll also learn about the normal forms, 1, 2, 3 normal forms, BCNF, and 4 normal forms. Also, we learn how normal forms can be transformed from lower normal forms to higher normal forms. Moreover, students will learn that normalization and ER modeling are used concurrently to produce a good database design. And we'll look at some situations where denormalization is used to generate information efficiently. Database tables and normalization. The table is the basic building block of database design. Consequently, the table structure is of great interest. Entity relationship or ER modeling yields good table structures. Yet, it is possible to create poor table structures even in a good database design and in a good table. So how do you recognize a poor table structure? And how do you produce a good table? The answer to both the question involves normalization. Normalization is a process for evaluating and correcting table structures to minimize data redundancies, thereby reducing the likelihood of data anomalies. Normalization works through a series of stages called normal forms. The first three stages are described as first normal form, 1 and F, second normal form, 2 and F, and third normal form, 3 and F. From a structural point of view, second normal form is better than first normal form, and 3 normal form or the third normal form is better than the second normal form. For most purposes in business database design, third normal form is as high as you go in the normalization process. However, you will discover that properly defined third normal form structures also meet the requirements of fourth normal form. The highest level of normalization is not always the most desirable. Although normalization is very important in database design, and it is an important database design ingredient, you should not assume that the highest level of normalization is always the most desirable. Generally, the higher the normal form, the more relational join operations are required to produce a specified output, and the more resources are required by the database system to respond to the end user queries. A successful design must also consider end user demand for fast performance. Therefore, you will occasionally be expected to denormalize some portions of a database design in order to meet performance requirements. Denormalization produces a lower normal form, that is 3NF, or the third normal form will be converted to a second normal form through denormalization. However, the price you pay for increased performance through denormalization is greater data redundancy. The need for normalization. Normalization is typically used in conjunction with entity relationship modeling. There are two common situations in which database designers use normalization. One, when designing a new database structure based on the business requirements of end user, the database designer will construct a data model. After the initial design is complete, the designer can use normalization to analyze the relationships that exist among the attributes within each entity to determine if the structure can be improved through normalization. The second situation is alternatively, database designers are often asked to modify existing data structures that can be in the form of flat files, spreadsheets, or older database structures. Again, through an analysis of the relationships among the attributes or fields in the data structure, the database designer can use the normalization process to improve the existing data structure to create an appropriate database design. The normalization process. In this slide, let's talk about how to use normalization to produce a set of normalized tables to store the data that will be used to generate the required information. The objective of normalization is to ensure that each table conforms to the concept of well-formed relations, that is, tables that have the following characters. Each table represents a single object. For example, a course table will contain only data that directly pertain to courses. Similarly, a student table will only contain data about students. No data item will be necessarily stored in more than one table. In short, tables have minimum controlled redundancy. The reason for this requirement is to ensure that the data are updated in only one place. The next characteristic is that all non-prime attributes in a table are dependent on the primary key. The entire primary key and nothing but the primary key. The reason for this requirement is to ensure that the data are uniquely identifiable by a primary key value. The next characteristic, each table is void of insertion, update, or deletion anomalies. This is to ensure the integrity and the consistency of data. To accomplish the objective, the normalization process takes you through a series of steps that lead to successfully higher normal forms. The most common normal form and their basic characteristics are listed in table 6.2. Students are requested to go over the forms. Students are requested to go over the table and try to learn the normal forms and their characteristics. The normalization process continued. The next set of characteristics is that from the data modeler's point of view, the objective of normalization is to ensure that all tables are at least in third normal form. Even higher level normal forms exist. However, normal forms such as fifth normal form and domain key normal form are not likely to be encountered in a business environment and are mainly of theoretical interests. More often than not, such higher normal forms increase joins, which causes slow performance. And moreover, it adds data redundancy. Some very specialized applications, such as statistical research, might require normalization beyond the fourth normal form, but those fall outside the scope of most business operation. It is crucial to understand these concepts because they are used to derive a set of functional dependencies for a given relation. The normalization process works one relation at a time, identifying the dependencies on that relation and normalizing the relation. Normalization starts by identifying the dependencies of a given relation and progressively breaking up the relation or table into a set of new relations based on the identified dependencies. Conversion to first normal form. Because the relational model views data as part of a table or a collection of tables in which all key values must be identified, repeating groups may be identified. A repeating group derives its name from the fact that a group of multiple entries of the same type can exist for any single key attribute occurrence. A relational table must not contain repeating groups. Normalizing the table structure will reduce the data redundancies. If repeating groups do exist, they must be eliminated by making sure that each row defines a single entity. In addition, dependencies must be identified to diagnose the normal form. Identification of the normal form will let you know where you are in the normalization process. The normalization process starts with a simple three-step procedure. So let's have a look at these steps. Step one, eliminate the repeating groups. Start by presenting the data in a tabular format where each cell has a single value and there are no repeating groups. To eliminate the repeating groups, eliminate the nulls by making sure that each repeating group attribute contains an appropriate data value. Step two, identify the primary key. Must uniquely identify attribute value. New key must be composed. Step three, all dependencies are depicted in a diagram, also known as dependency diagram. What is dependency diagram? Dependency diagrams are very helpful in getting a bird's eye view of all the relationships among the table's attributes, and their use makes it less likely that you will overlook an important dependency. Note that figure 6.3 includes the relational schema for the table in first normal form and a textual notation for each identified dependency. Still on conversion to first normal form, the term first normal form 1 and F describes the tabular format in which all of the key attributes are defined. There are no repeating groups in the table. In other words, each row or column intersection contains one and only one value, not a set of values. All attributes are dependent on the primary key. While partial dependencies are sometimes used for performance reasons, they should be used with caution. If the information requirements seem to dictate the use of partial dependencies, it is time to evaluate the need for a data warehouse design. Such caution is warranted because a table that contains partial dependencies is still subject to data redundancies and therefore to various anomalies. The rate redundancies occur because every row entry requires duplication of data. Conversion to second normal form. Converting to second normal form is done only when the first normal form has a composite primary key. If the first normal form has a single attribute primary key, then the table is automatically in second normal form. The first to second normal form conversion is simple, starting with the first normal form format displayed in figure 6.3. These steps are followed. Step 1, make new tables to eliminate partial dependencies. For each component of the primary key that acts as a determinant in a partial dependency, create a new table with a copy of that component as a primary key. While these components are placed in the new tables, it is important that they also remain in the original table as well. It is important that the determinants remain in the original table because they will be the foreign keys for the relationships that are needed to relate these new tables to the original table. For the construction of our revised dependency diagram, write each key component on a separate line. Then write the original key, that is a composite key, on the last line. Step 2, reassign corresponding dependent attributes. Use figure 6.3 to determine those attributes that are dependent on the partial dependencies. The dependencies for the original key components are found by examining the arrows below the dependency diagram shown in figure 6.3. The attributes are dependent in a partial dependency are removed from the original table and placed in the new table with its determinant. Any attributes that are not dependent in a partial dependency will remain in the original table. In other words, they are eliminated. The results of steps 1 and 2 are displayed in figure 6.4. At this time, most of the anomalies identified earlier have been eliminated. Do note that figure 6.4 shows a transitive dependency which can generate anomalies as well. Try to compare figure 6.3 and figure 6.4 and see the differences. Conversion to second normal form continued. A table is in second normal form when it is in first normal form and it includes no partial dependencies, that is, no attribute is dependent on only a portion of the primary key. Note that it is possible for a table in second normal form to exhibit transitive dependency. That is, the primary key may rely on one or more non-prime attributes to functionally determine other non-prime attributes, as indicated by a functional dependence among the non-prime attributes. Conversion to third normal form. Step 1. To further eliminate data anomalies, the following steps must be taken. For every transitive dependency, write a copy of its determinant as a primary key for a new table. A determinant is any attribute whose value determines other values within a row. If you have 3 different transitive dependencies, you will have 3 different determinants. As with the conversion to second normal form, it is important that the determinant remains in the original table to serve as a foreign key. Step 2. Place the dependent attributes in the new table with the determinant in step 1 and remove them from their original tables. Check all the tables to make sure that each table has a determinant and that no table contains inappropriate dependencies. In this case, table job in figure 6.5 seems appropriate. Check all of the tables to make sure that each table has a determinant and that no table contains inappropriate dependencies. When you have completed these steps, you will see the results in figure 6.5. In other words, after the third normal form conversion has been completed, your database will contain 4 tables. Project with the attributes project number and project name. Employee table with the attributes employee number, employee name, and job class. Job table with the attributes job class and charge hour. Assignment table with the attributes project number, employee number, and assigned hours. Note that this conversion has eliminated the original employees table's transitive dependency. The tables are now set to be in the third normal form. Improving the design. The table structures are cleaned up to eliminate the troublesome partial and transitive dependencies. Next is to focus on improving the database's ability to provide information and on enhancing in operational characteristics. Do remember that normalization cannot by itself be relied on to make good designs. Improving designs is very valuable because it helps eliminate data redundancies. Issues to address in order to produce a good normalized set of tables. The list is provided in the slide. First of all, evaluate primary key assignments. Then evaluate naming conventions. After that, refine attribute ethnicity, identify new attributes, identify new relationships, refine primary keys as required for data granularity, maintain historical accuracy, and evaluate using derived attributes. Higher level normal forms. Tables in three normal form will perform suitably in business transactional databases. However, there are occasions where higher normal forms are useful. Two special cases of third normal form include voice code normal form, BCNF, and fourth normal form. The voice code normal form. A table in the voice code normal form when every determinant in a table is a candidate key. Most designers consider the voice code normal form to be a special case of third normal form. Now, voice code normal form has same characteristics as primary key, but for some reason, not chosen to be the primary key. When table contains only one candidate key, the third normal form and the voice code normal form are equivalent. The voice code normal form can be violated only when table contains more than one candidate key. In fact, if the techniques shown here are used, most tables conform to voice code normal form requirements once the third normal form is reached. So how can a table in third normal form and not be in voice code normal form? To answer that question, you must keep in mind that a transitive dependency exists when one non-prime attribute is dependent on another non-prime attribute. In other words, a table in a third normal form when it is in second normal form and there are no transitive dependencies. But what about a case in which a non-key attribute is the determinant of a primary key attribute? That condition does not validate the third normal form. Yet it fails to meet the voice code normal form requirements because voice code normal form requires that every determinant in the table be a candidate key. Fourth normal form is a table in which a table is in fourth normal form when both of the following are true. It is in the third normal form and no multiple sets of multi-value dependencies are available. Fourth normal form is largely academic if tables conform to the following two rules. All attribute dependent on primary key is dependent of each other. No row contains two or more multi-valued facts about an entity. Normalization should be part of the design process. That is why normalization and database design are very important. Therefore, make sure that the proposed entities meet the required normal form before the table structures are created. The likelihood of data anomalies will be small, but even the best database designers are known to make occasional mistakes that come to light during normalization checks. However, many of the real-world databases you encounter will have been improperly designed or burdened with anomalies if they were improperly modified over the course of time. Therefore, you should be aware of good design principles and procedures as well as normalization procedures. If you are aware of them, you may be asked to redesign and modify existing databases. To have a good database design, first an ERD is created through an iterative process. You begin by identifying relevant entities, their attributes, and their relationships. Then you use the results to identify additional entities and attributes. The ERD provides the big picture, a macro view of an organization's data requirements and operations. Second, normalization focuses on the characteristics of specific entities. That is, normalization represents a micro view of entities within the ERD. The normalization process might yield additional entities and attributes to be incorporated into the ERD. Therefore, it is difficult to separate the normalization process from the ER modeling process. The two techniques are used in an iterative and incremental process. Denormalization. It's important to remember that the optimal relational database implementation requires that all tables be at least in third normal form. A good relational database management system excels at managing normalized relations, that is, relations void of any unnecessary redundancies that might cause data anomalies. Although the creation of normalized relations is an important database design goal, it is only one of many such goals. Good database design also considers processing or reporting requirements and processing speed. The problem with normalization is that as tables are decomposed to conform to normalization requirements, the number of database tables expands. Therefore, in order to generate information, data must be put together from various tables. Joining a large number of tables make additional input or output operations and processing logic, thereby reducing system speed. Most relational database systems are able to handle joins very efficiently. However, rare and occasional circumstances may allow some degree of denormalization, so processing speed can be increased. Normalization purity is often difficult to sustain in the modern database environment. Lower normalization form occurs in specialized databases known as data warehouses. Specialized databases reflect the ever-growing demand for greater scope and depth in the data on which decision support systems increasingly rely. You will discover the data warehouses routinely uses second normal form structures in its complex, multi-level, multi-source data environment. In short, although normalization is very important, especially in the so-called production database environment, second normal form is no longer disregarded as it was. Although second normal form tables cannot always be avoided, the problem of working with tables that contain partial and or transitive dependencies in a production database environment should not be minimized. Aside from the possibility of troublesome data anomalies being created, unnormalized tables in a production database tend to suffer from these defects. Data updates are less efficient because programs that read and update tables must deal with larger tables. Moreover, indexing is more cumbersome. It is simply not practical to build all of the indexes required for the many attributes that might be located in a single unnormalized table. Unnormalized tables yield no simple strategies for creating virtual tables known as views. Data modeling checklists. You have learned how data modeling translates a specific real-world environment into a data model that represents the real-world data, processes, and interactions. The modeling techniques you have learned thus far give you the tools needed to produce successful database designs. However, just as any good pilot uses a checklist to ensure that all is in order for successful flight, The data modeling checklist shown in the next slide assists the database designers. Students are requested to go through the checklist and get well versed with these lists. Summary. Normalization minimizes data redundancies. First three normal forms, first normal form, second normal form, and third normal form are most commonly encountered. Table is in first normal form when all key attributes are defined. All remaining attributes are dependent on primary keys. Table is in second normal form when it is in first normal form and contains no partial dependencies. Table is in third normal form when it is in second normal form and contains no transitive dependencies. Table that is not in third normal form may be split into new tables until all the tables meet third normal form requirements. Normalization is important part, but only part of the design process. Table in third normal form may contain multi-valued dependencies, numerous null values, or redundant data. Convert third normal form table to fourth normal form by splitting table to remove multi-value dependencies. Tables are sometimes denormalized to yield less input or output, which increases processing speed. Thank you for listening to the lectures on normalization. Thank you.